So let's dig into the new material. We're going to move into chemical kinetics, or basically we're going to be looking at speeds of reactions. So we've got two directions we can go in. We've got thermodynamics and we've got kinetics. If you think about a trip that you're going to take, thermodynamics tells you your destination. Where will you end up? Kinetics is going to tell you how fast the reaction will occur, how long it's going to take to get there. So thermodynamics is going to tell you about the destination, but kinetics tells you about the journey. So we are going to focus on the kinetics aspect in this new material and in lab for the next couple of weeks. So when we start out thinking about chemical kinetics, we're going to be talking mainly about rates. So when you think about rates, they don't just apply to chemistry. The speed your car goes is an example of a rate, 55 miles per hour. It's a change in a unit over a change in time. So if we focus on a particular chemical reaction, like A goes to B, we can think of rates in terms of the change of a concentration. So in this case, brackets are going to stand for concentration. Specifically, brackets are going to mean molar. Remember, molar has the unit capital M. So our rate is going to be the change in concentration of A over the change in time. And just thinking about what A is on the reactant side of the reaction. So it's being consumed. So we can look at a rate of consumption, or how fast A is being used up. We can also look at the rate of production. So if we focus instead on B, then we can look at the rate expressed in terms of a change in concentration of B over a change in time. Now, rates can be in terms of per second, per minute, per hour. It just depends on what the appropriate time period is. Now, note that rate is negative when we put it in terms of a reactant, but that negative sign is missing when we get down to expressing rate in terms of a product. We'll be explaining this in just a few minutes, but keep that in mind. Now, we've got a plot of that reaction we were just looking at in terms of A going to B. So this is our reaction. A is a reactant, and B is a product. So when we look at A is decreasing. So the amount of A that we've got, because of the direction of the curve is headed downwards. So the number of molecules that we've got of A are going to be decreasing over time. If we look at B is increasing over time. If you look at the amount of B on the plot, the number of molecules is increasing. That's because we're producing B. So, rates are always going to be expressed as a positive. Chew on this for a second. If you look at the change in number of A molecules over time, it's decreasing. So the change in A over time would be negative. If you think of it almost like a slope, because this is headed downwards, this would be a negative slope. So if we want to express rate as a positive value, then whenever we express rate in terms of a reactant, we have to include that negative sign out front. That makes the rate overall positive. We don't need to include a negative sign when we express the rate in terms of a product, because we're already producing a positive amount. So, moral of the story, we always express rates in terms of a positive. Okay, so observed reaction rates. That means the speed that we actually see in the reaction is related to the stoichiometry. So if you think back to stoichiometry, we had these guys out front, these big numbers, not subscripts, but coefficients. Now, coefficients are everything when we talk about observed reaction rates. If we want to look at relative rates, which means comparing one chemical or one substance involved in the reaction to another, the coefficients play the biggest role. So in this first question, what are the relative rates of B and A? So what are the relative rates of our one reactant and our one product? This is like saying, relative to A, how fast is B going? Now, think about this for a second. For every one A that is consumed or used up, how many B's are produced? Well, there's one. We would say that A and B are in a 1-to-1 ratio. So because for every A consumed, there's a B produced, we got equal rates. So, equal coefficients, equal rates. If we move on to our second example, we don't have equal coefficients anymore. So, let's pretend that 10 seconds of this reaction have passed. So I'm going to put 10 seconds over here and 10 seconds over here. Now, in that 10 seconds, let's say that 1 C is used up. Well, in that same 10 seconds, if 1 C is used up, how many B's will be produced? Well, 2 B's would be produced because we have a 1-to-2 ratio. So if we look at the relative rates, 2 over 10 works out to 0.2, and 1 over 10 works out to 0.1. So we'd say C to D is a 1-to-2 ratio. So D has to be produced 2 times faster. Or, for every 1 C consumed, 2 D are made. So D is double the rate that C is consumed. So, let's generalize this. We need to be able to write out rate expressions, or ways to write out the rate in terms of reactant and product. So, this is a typical problem. If I were to ask you for rate expressions, this is how we would approach it. So, rate is a change in concentration of A divided by change in time. And we've got to remember to include that negative sign because A is a reactant. Reactants get that negative sign out front. And we divide this rate by whatever the coefficient of A is. Now, if we were to do this for C, we would still have our change in concentration of our product divided by change in time, and we still include our coefficient, but we do not include a negative sign because products in the rate expression don't get negative signs. So, let's do a little bit of substitution. If we look at a change in concentration over a change in time, well, that's just a rate. So, going in here, we've got rate. Actually, let's cross this little guy out. He doesn't need to be there. Rate, we're just taking to be change in concentration over change in time. So we get rate of A equals that negative sign because A is a reactant divided by its coefficient. We get the rate of C not having the negative sign because C is a product divided by its coefficient. So far we haven't really put this too much into practice, so let's do a practice problem. We've got a reaction. 2A goes to 1B. And we know that 2 moles of A, based on the coefficient, disappear or are consumed for each mole of B that is produced or formed. So, let's write out our expression. The negative of the change in concentration of A divided by the change in time, that gives us the rate of A, but then we also have to include the coefficient, the 2, and the negative sign because this is a reactant. We're also going to include the rate in terms of B. Change in B over a change in time, and the coefficient is included, but it's just a 1, so it doesn't show up directly in the rate expression. So, what we can pull from this is that the rate of appearance of B is half as fast as A's consumption. Now, just backing this up a touch, looking at our coefficients, for every 2 A's that are consumed, 1 B is produced. So in the time that 1 B is produced, 2 A's had to be used up. That means A is being consumed 2 times faster than B is being produced. Or thinking about it in terms of B, B is being produced half as fast as A is being consumed. And it all deals with the coefficients. So let's write out the rate expression in this top problem for this reaction. Let's start out going chemical by chemical. So we'll start with CH4. We need a change in CH4 over a change in time. We include our negative sign because this is a reactant. We include the coefficient of 1 that's in front of the CH4. And now we have a rate in terms of methane, CH4. Our next step is to look at O2. We get a change in O2 over a change in time. We include the negative sign because it's a reactant. We include a 2 because the 2 is the coefficient. Now, that's all our reactants. Now we need to worry about products. So CO2. Change in CO2 over change in time. We include the 1 because the 1 is the coefficient of the CO2. And no negative sign because this is a product. All right, and we finally got H2O. H2O has a coefficient of 2, so 2 shows up in the denominator. And we have our change in water over change in time. So, what we've got here is a rate expression that shows for this given reaction. Now, if we had a reaction like this, we wouldn't normally write out the rate expression for all 4 of the reactants and products. We'd mainly focus on just what we were interested in. And what we're interested in depends on the particular problem. So let's start the second problem. The second problem asks us about rates of decomposition and rates of formation. So we know the rate of HI. It says the rate of decomposition, or the rate of breakup of HI, is 5 times 10 to the minus third molar per second. And it asks, what is the rate of formation of H2? So we know HI, and it's asking about the rate of H2. So this is a relative rates problem, and in relative rates problems, it's good to look at the rate expressions. So let's kick this off. If we were to write the rate expression for HI, we would want the change in concentration of HI over the change in time. We're going to divide by 2, because 2 is the coefficient for HI. And we put the negative sign out front, because the negative sign is there because HI is a reactant. We're going to set that equal to the rate expressed in terms of H2, which is the change in H2 over time divided by the coefficient of H2, which is 1. We're going to make our substitution saying that change in concentration over change in time is just a rate. So we're going to say the rate of HI over 2 equals the rate of H2 over 1. Now, we know one of these two rates. Look at the original problem. The rate of decomposition of HI is 5 times 10 to the minus third molar per second. So we know this rate. We can solve for the rate of H2 just by plugging in. So I'm going to plug in 5 times 10 to the minus third in for my rate of HI. So I end up with 5 times 10 to the minus third divided by 2 is going to equal the rate of H2. So we get an answer of 2.5 times 10 to the minus third molar per second. Now, let's back this up a second and just think about the logic behind this problem. Now, we're given the rate of decomposition of HI. It's 5 times 10 to the minus third molar per second. But let's just focus on the reaction. We're relating HI to H2. Let's look at the coefficients. For any given unit in time, for every 2 HIs that are used up, we're going to make 1 H2. So, HI is going to be used up 2 times faster than H2 is produced. So let's see if our answer lines up. HI is produced 2 times faster, or 5 times 10 to the minus third molar per second, compared to H2's rate of production, which is 2.5 times 10 to the minus third molar per second. So this holds true with the coefficients. The coefficients line up with what we see in the rates. Thanks for watching.